Oh, great. Okay. Okay. I'm glad people are actually hearing me. Okay, so that would be bad if I have recorded a lot of stuff without actually saying what I'm doing. Anyways, so next step is I want to go back to this advent of code problem, and I forget which day it was. Whichever advent of code. So actually I'm in my advent of code repository. I forgot about that. So there should be like a problems folder, inputs folder, inputs. I forget which day it was. Amphipods, Dijkstra. Well, okay, so I want to say it was like day 15 or 16 because I want to find the specific inputs from advent of code and then test the outputs and test that this actually worked. So let me, okay, so Amphipod third and second. I'm seeing this probably the second day, or the second module, which is completely arbitrary. Okay, I did at least sort the file into different days. So polymer is polymer the. Okay, so we have Dijkstra down here. Okay, chain, that sounds familiar. Okay, day 15, I think is correct. So okay, so that looks reasonable. Final. Okay, great. And the day 15 final in particular is good because it's a very, it's a nice big beefy test case. Although I will also need to, whoops, nope, not the other day. The other thing I wanted to do was verify my answers here, so using the full map. So I think we actually get 3. So we have this basic example, we have the more complicated example, and then we have the final example. Okay, so we have 3 test cases, and I want to incorporate this all into my tests here. So let's say AOCD1, or AOC case 1, and this is actually going to be Graph2D. I'm actually gonna. I should have changed the other case to use double because this case is actually going to use ints. I'm actually going to go back to using ints. Just so that's easier. What did I miss? Here. Okay, next up. Nope, still not there. Someone still thinks this is an array of doubles. Here it is. Okay, cool. So, case 1. We need to do, I need to incorporate my function here where I actually read 2 digits. That's actually, I did make a generic function for that way back when. That's good. Oh, lib. Oh, this takes a file path. I kind of want to just do the string because what I want to do in my tests is have case 1 is this one. Hopefully this works. I keep doing Command C because I often use this keyboard for my Pretty low. Okay. Whoa. That wasn't what I wanted to do. Come on. Multi-line strings are... Oh, there's also... It's also... I would have to put in new lines. Okay, we're just going to do this other way. AOC case 1. So we want to do read 2D digits. And put slash. Oh, this is the basic case. Oh, that's interesting. Wait, this is the basic case. This is the big case. Where's the medium case? The total risk of this, okay. So this is, okay, so for the second part, we take the starting graph and then we expand it 5 times in this weird way. I'm not sure I'm going to do part 2. Or at least I'm going to take part 1 and do the basic case gives me 40 and the more advanced case gives me 447. I can do those cases easy enough. I don't know if I have, I probably do have a handy function that sort of made the graph bigger. Augment risks. What is the distance array? Did I type that? Yes, I did. So we actually we can still do this. It's we need lib and then we need to import second, which is going to give us augment risks. Okay, and after that, what is next? I need to make what do I need to do? Also, I want to wrap all of these in graph2D. Or wait, why don't I just... No, I do want it to be 4. That's a little tedious, but it'll work. Let's just bring that down. And now, see day 15, 1, find shortest distance, case 1. Ooh. I need my bounds, I need my starting positions, which the first few it's easy enough to do. Well, actually not really. Okay, for the very first case, I think it's easy enough to do 1, 2, 3, 6, 7, 8, 9, 10, so it's just 0, 0, 9, 9. The next one is quite a bit bigger, and I'm not totally sure. But we'll start with this just to make sure it's working, and that should be equal to a distance of. Let's double check this answer again. So the very first basic case should be 40. So it's 40, and let's see if that worked or if it's going to complain at me. I missed a parenthesis. Okay, it does not exist. Inputs, it's inputs. Okay, so that part worked. Except I actually just want to print how large. Well, actually, I can do. Case 3 is actually going to be 0, 0, and then I think it's just 49, 49. I think that's right. And the distance is going to be, in this case, 315. Took a little time there. I can't wait till our final case. So our final case, or bigger cases. We need to print out how long this is. And then, or I could just. If I could open it up, actually. I can see the line count. The line count is 100, so it should be 100 by 100. Let's say 9L, 9H, 8L. Okay, yeah. So the other case is 100 by 100. So we just need to change our dimensions here. So it's 9999. And the final distance in that case is going to be 447. And then case 4, it's going to be 5 times that, so it should be 499, 499, and it should be this rather larger number, 2825. See how long that takes, because that might take a little while. That's a very large case. It didn't take that long, 2.5 seconds. It's a pretty good implementation. Okay, so those cases work. So I've actually verified my my Dijkstra's algorithm on test cases that I did not create, because when I create test cases, they tend to be absurdly simplistic. Okay, run those tests. Okay, so the second problem from Advent of Code last year that used Dijkstra was, I want to say it was like, I remember it used the word like amphipod or something. I feel like it was day 22, maybe? No, it wasn't this one. That was a hard one. 23, amphipod, day 23, okay. So this one turns out to be Dijkstra's algorithm, and it's quite complicated. but I can start making these test cases at least. Well, kind of. I know which day it was. It was day 23. Okay, so I know it's day 23. Add tests. So even adding tests is going to be hard without doing some of this original work. I think I'm going to skip to this step 5. So now that we have a good battery of test cases, we can actually modify our algorithm so that we don't have to enumerate the state space. So this is going to be a refactoring step. I actually might want to commit my work so far. Things might get a little messy here. Okay, so what do we want to do here? So what I've put in this type family, we have this idea of Dijkstra nodes, where we enumerate all of the nodes in our graph. And this is not necessarily, like, it in a, one way to write Dijkstra's algorithm, it helps to have this. But you should also still be able to do it without necessarily enumerating the entire state space right there. Like, the only function we should really require is this edges function, which says, okay, given I'm, given my graph, and given I'm at one particular node in my graph, give me all of the adjacent nodes and their distances. I shouldn't need to enumerate all of the nodes at a particular point. So where do I use that in here? And it comes with making my initial distances in the initial queue. Because the initial queue has, basically it sticks everything in there with a priority of infinity, where minimum is better, so infinity is a very low priority. And our hash map initially assigns a distance of infinity to everything as well. So how can we do this so that we don't actually need this step? And basically what we want to do is say, okay, this should be empty. Our initial distance map should be empty. We don't have any distances in here, except for source. We do know source. So we say hm.singleton, and it'll be source dist 0. That's the only one that should be in our initial distance map, and the same thing can be said for our initial, actually no, our queue. Oh yeah, actually yeah, the queue, yeah, it does have this. So our queue should be similar in that it should be singleton with we flip them, so it's dist 0 and source. Okay, and in this way, so now we aren't enumerating our entire state space, but this affects our algorithm down the road. What needs to happen in some of these other cases? So this is fine. Like, we handle the case where the queue could be empty. We just, give our existing distance map. Everywhere where we use this operator, the bang operator, to access in our hash map, I think we need to be more careful. We need to use a different operator, which essentially says, okay, given I have a hash map from anything to anything. I almost want to say this should be arbitrary. We can say just any type A to a graph dist on A. not even A, just any graph distance. Like this can be a very generic function. I just want to call this get safe. So we say hash map, we put sage instead of safe. So hash map and then an A key, get safe A produces, actually maybe, do I want to actually just make my own operator? I'm just going to call this, I would really like it to be an operator, because that just, it's a little more, it's just a little more simple. So the point of this function is that we can always use infinity as our fallback if we don't have it in our map. So you know, map and key. So we say case. I forget if hash maps have that particular operator. That's kind of the thing with, like, these Haskell data structures follow a general pattern, but there are just a few exceptions, and this might be like one of them, where it's like, okay, so it does have this, where we can actually use this. I feel like one of them might not have that operator. But anyways, so if we try to access the key, and nothing's there, we just return infinity. And if it's just something, then it's just X. So we're fine. So as long as I do that here, and in maybe some other places, where else do I need it? Here. Except now it's no longer a hash map function, of course. Go back and change a few things. Modify everything is actually going and needing to compile some things. Okay, h dot single. Oh wait, h no h. Wait, yes. Wait, is this one? Is this right? Oh wait, is that not how heaps work? Singleton function might be a little weird in heaps. We just get, we get a single, okay. I think it's just, I'm just gonna use from list, even though it's a new one. Because the singleton is confusing me. Oh, not you. No, you're fine. Okay, we want to say h.from list. No instance for equals. Okay, I just need a few more constraints here, which should be acceptable constraints. Might also need hashable. We'll see if it asks for hashable. Yeah, we also need hashable. But we already have those constraints. Shouldn't be a problem. Okay, so that works. And now let's go ahead and run that test command. Okay. So it doesn't seem to have made a big difference on the runtime, but everything still works. And the more important part of all of this, the win that we sort of get here, is, I'm actually just going to go ahead without type signature here. I don't think there's a reason not to. So now our big win is that we can take out Dijkstra nodes, and everything should still work. Okay, so that still compiles and the algorithm still runs. Okay, so that's an improvement. Now I want to start thinking about this this next problem, because the point is the point of doing that is that for this next problem, enumerating the state space, the entire state space is non-trivial. Or I should say the entire node space. So all the different nodes that we can occupy in our graph, it's a lot. And so the basic idea with this problem is, we have these A's, B's, C's, and D's in these little slots. We want to move all the A's to be in the first slots, the B's to be in the second slots, and the C's to be in third slots, and so on. There are very particular moves that you can make, like each one either goes into the hallway and then comes back. It doesn't move from the hallway to the hallway. They don't cross over each other ever. So there are a lot of very distinct rules about how these can move within this hallway, which makes it, which limits the state space a fair amount, but it's still a rather large state space. But it's still searchable if you use something reasonably efficient like Dijkstra's algorithm. So we have to think about, okay, we should be able to define this just by saying, okay, what is our type? So what's, the amphipod type, maze type, I don't know. And then we need to define, okay, what's our distance? What is our node? And then what we need to do is we need to define, okay, what are the edges? And so now I have to go and take a look at my code. I forget, because I have a specific module for this. I think this was my final module. Where am I passing a state to? Oh, I see. I'm just, that's actually kind of useful. So we have the names for everything. So I'm not even going through the trouble of parsing a file here. I just copied the file contents essentially right here. But okay. So what does a state look like? Because these ultimately are the nodes we're using, I think. So we have 4 rooms. Each of them contains, the amphipods. And there are a certain number of hallway slots. And then we also have this idea of a room size. And that is constant over the course of the problem. But this is our possible moves function. This takes one particular state and gives us, well, why are you giving me a string? It's a little weird. If not null. Okay, well, that's something else. Maybe that's a debugging thing. And then we have this very convoluted logic. Oh my gosh. It's a lot. Oh my gosh, it's a lot. Because so this problem, like the logic you have to write for the state evolution, it's quite complicated. A lot of this is copy pasted, but it's still, you have to be very careful in how you copy paste it. And I just provide, I think the string is, I'm just saying what the move is. But we are almost there. So one particular state is a node. The question is, do we need anything that is like a graph? Do we actually need a graph type? And I'm not sure we actually do. Like, can I say, okay. So we want to say new type and graph equals, like we could maybe just get away with unit here, I'm not sure. And we want to say instance Dijkstra graph of amp graph where. Okay. Type Dijkstra node. Oops. Isn't it? Distance. Isn't it? Node is actually absolutely non-int. Amp state, we're importing that. This is just my test here. Or wait, maybe I should, instead of doing all this junk in here, I should do it in the amphipods. I should go to amphipods. I should import Dijkstra, not the other way around. Not sure I didn't do that. Okay, so let's go ahead. D amphipods. So the node, each node in our graph is this state object. The distances are measured in ints. And now the other ingredient we need is, how does the state evolve from one node to the next? And that, I believe, we have essentially covered. So Dijkstra edges graph state is equal to, so yeah, the string is just for debugging. So we'll say possible moves. And map lambda something over our moves. So given, we don't care about the string. I believe this is giving us distance and state. And what we ultimately want here is brain's not working. We need the node first and then the distance. So we need the state and the distance. Okay, so the first, so we don't have any notion of a graph because we sort of have we have a notion of, you know, like our only graph is the nodes themselves. So we're not necessarily, each state is essentially self-contained. We're not referring back to a previous graph. Like if we had some sort of state information, like we needed to track like how many times each one had moved for some reason, that's something we could store in our graph if we wanted to, I guess, but not really actually. That would need to be in the node. That would need to be in the state because we never change our graph. This is essentially an irrelevant argument. So let's just see first if this compiles. Okay, it does not. Ambiguous, whoops. Ambiguous reference to Dijkstra state. Okay, let's right. Let's say import qualified. We're gonna have to qualify a bunch of stuff, but let's save us some grief. I think that's okay. Qualified, is that not acceptable? What if we say that? Is that okay? Legal. Okay, we have to start using title extensions. Let's just go ahead and bring all the. If this doesn't immediately work, let's go ahead and bring. Oh, it works. Okay. So to make the actual instance itself, we didn't need to do that much. So. So my new solve amp is equal to what? This takes a starting state. It returns an int. And what is that? So, well, the thing is we need to, without, well, I don't know, it's not that hard to define what our final state is. So the original thing we do, or we can define what the final state looks like, right? Because we just have, you know, we get the room size from our original state here, right? So we got room size, you know, final state equals replicate for amber, replicate, not for RS. Bronze is the second one, the B. Does it. So that's that stuff, and then we just want a bunch of nothings. And the room size. That's our final state. We want to say raw dist and find shortest path. Even though we're not finding the shortest path, we're just finding the far shortest distance. Find shortest distance, yeah, I named it appropriately. I should put on here a modification. I'm going to make this my next note here. Allow returning the full path. That's an extra little flourish we can add if we want to. It kind of, yeah, I mean, yeah, it'll be a second type signature, I guess. trying to decide if we need to sort of rewrite everything or if it's just, you know, we track the path and then we drop it. Probably that. But anyways, find shortest distance. So final dist should be, we don't actually, shortest distance, start state, final state, you know, graph, which is just an arbitrary thing. And let's see if that compiles. No instance for, oh, that's right, I need to make this hashable, which is weird, but I'm actually wondering if making it orderable, like making the whole algorithm orderable, it would be ultimately better for performance. I'm going to test that later, but this should be okay. We need to import data hashable clearly. Wait, what? Wait, really? I can't do that? No. I don't need to derive any class hashable. If this gets any worse, I might need to did I do that here? Did I include general? Oh yeah, general. Well, that's still not what I'm doing exactly. Or was I just using I bet I was just using hashable types anyways. Possible fix uses standalone deriving instance. Right. Okay. So no instance for generics. I don't think generalized new type deriving is gonna help me. I can try, but generics is probably actually what I have to do here. Yeah. Help. So I have to go and import generic. We have to say what deriving generic. And for here and here, is that going to work? No instance for generic. What? Okay, I thought I did put that there. Need derived generic. Okay, and that compiles. So we've won that round of compiler extension bingo. Okay, so this is exciting because we already have our initial states, like A state 1 and A state 2 are the two ones we have here. So A state 1, like we have or actually here, I can do so okay, let's go to Dijkstra tests. Solve amp case 1. And what what distance should this be? This is actually going to be an int. I'm just doing the raw stuff. So this very first simple case is 1251. Or sorry, 12521. Case 2. And this is the case that I actually got. Ends up being 10526. In these other cases, we expand everything. 44,169. And our final answer was 41,248. And it might take some time to solve these. This is not necessarily like this. It's a tricky solution, so I'm not sure. Or it's a large state space, so it might take some time to solve these larger cases. So I need to define what these cases are, except that I have some of them predefined. So, okay. Let me look at input / day 23. Yeah, so day 23 basic. We had, okay, so this is bronze, amber, copper, is there bronze, copper? Okay, so this is A state test 2 is that first one. This is just the basic. Oops. Get rid of all that. Oops. The other one. So A state 1, I believe, covers my final. Copper, bronze, amber, amber, desert bronze, desert copper, yes. So A state 1 will cover this case. Now I believe this one, A state 2, is this. I believe this is my final one, so I think I can do A state 2 here. Whereas theirs, maybe I didn't do that for theirs, so I can say I want to say A state test 3. Because this one has a room size of 4, and what's its initial configuration? So BDDA. Okay. Right? Oh, what? No, apparently not. Apparently I'm doing this wrong. What? Oh, I see, I see. Okay. And then this case should be okay. Let's Let's see what happens. Nope. Solvamp. Oh, what? Solvamp has to... No. Solvamp. New solvamp. The first two cases worked. The second case did not work. I wonder if I just... They're close. Did I just mistranscribe this last one? Well, the last one should be 284. Yeah, okay, I just mistranscribed this last one. And now did I miss... this one, I'm saying 44169. That's their case, but did I do this right? Did I define the case properly? Bronze, does it, amber. Copper, bronze, does it. Bronze, amber, copper. Does it, amber, copper. Amber, it looks correct. Looks correct. Am I calling the right case here? This is A-state test 3. Huh. It's a little strange. I might need to do some deeper investigation in that. I'm not sure why that case isn't working. Because it looks like I have the correct input here. A-state test 3. And I think I should have the right output. The right output is update example 44169. What am I claiming? What is my algorithm claiming? 4727, which is substantially lower. So possible I have a bug in this implementation, but actually it's not. It wouldn't be too absurd for me to have a bug in the state evolution, to have a small bug, like I mistranscribed a number somewhere, could potentially result in an error in just one case, even though the other cases are working. So that's entirely possible. I would definitely put it down as that there's more likely a bug with this code than there is with my Dijkstra code. But I actually want to let me actually do this. So we can actually bring up GHCI. And I can do solvamp like the original, and I can do it on this task case that I didn't do before. Oh, oops. Oh, it wasn't on the row. But no, so this is taking a lot longer than it was in my test code, which, well, that might mean whatever Dijkstra implementation I did down here is slower. But the benefit of this function is that it prints everything out, it unwinds the path, it prints what our moves were, and so I can compare the moves that I'm sort of proposing to to what is proposed here. And again, yeah, I'm getting I'm getting the same smaller answer. So I'm curious. I'm gonna take. Actually, no. I'm gonna take here, and I'm gonna compare to. I'm gonna take this and put it over here. So you're saying d to h10. Wait, what? Oh. Well, already I see a problem with my logic. This set of moves doesn't seem possible. D-room to h10, if I am thinking about how I actually implement this, d-room to h10, d-room to h1, and then d-room to h11 doesn't seem possible. So there's some there is some flaw in that particular logic of this logic, this whole mess of stuff. But I don't believe that there is a problem with my Dijkstra's implementation. So I can dig into that case a bit more, I guess. But yeah, I think I'm going to leave the stream there for today. We will, so we got a test for that. While returning a full path, maybe some debugging. Yeah, so the next things we can sort of look at are, using ORD instead of hashable, which is honestly probably just better. It's a lot simpler to make an ORD instance just because it's stock derivable, and whereas hashable apparently is not. And I'm not sure, like, the theoretical performance gains of hashing versus using a binary tree, just the way that all happens in Haskell. I'm not sure as a practical matter that is going to be faster. But anyways, I will look into that. But thank you everyone who tuned in today. I will be back streaming again on Monday. Honestly, I don't know if it's going to be morning, afternoon, or evening. Mondays are a bit more variable, but yeah, hope to see you again. Thank you very much.